Okay, so thank you for introduction and thank you for inviting me. I am glad to have this opportunity to share my work here. So I am Ho Seung Song, an assistant professor in the Department of Industrial and System Engineering and Graduate School of Data Science. So this semester I'm teaching a course titled Statistical Inference for Data Science. So this is a graduate course for students in the Graduate School of Data Science. And I know students have diverse backgrounds. And I guess the audience here has diverse backgrounds as well. So when preparing this seminar, I was concerned what to include in this slide. So as you know, KAIST does not have statistics department, right? Of course, although my Department of Industrial Engineering, offers the most concrete statistics coursework at KAIST. So this is the same as the situation of MIT or Georgia Tech. But anyway, there are no students who major in statistics at KAIST. So as a statistician, today, I am going to talk about statistical decision making. So how statistics is applied in decision making, how it differs from AI and machine learning approaches, and introduce one of my research works related to this topic. So I would first say statistics play a key role in decision making because statistics relies on data-driven evidence. So instead of depending on intuition, we can make informed decisions based on data and insights. And second, statistics helps us understand variables, how they relate and how they interact with each other. And this understanding is essential for uncovering hidden patterns and making better predictions. And third, statistics allows us to critically evaluate our claims and conclusions. And this is a main point that I would say today. So let's focus on this part in more details. So then why does statistics play such a key role in decision making? The key reason is that decision making process always involves uncertainty. So for example, suppose that we would like to know whether the two variables, gender and Netflix subscription, are associated or not. So to check this, we conduct an experiment, collect data, and analyze it. And suppose we find that a certain gender has a higher subscription rate. Then can we conclude that these two variables, gender and Netflix subscription, are associated? Because of our result from experiment, data, and evidence, since a certain gender has a higher subscription rate, two variables, gender and subscription rate, seem to be associated. But can we confidently claim that this is a fact? What if a different data set gives another result? What if the sample size changes? Let me show an easier example. So suppose that we roll a 6-sided die 5 times and it shows 2 3 times. So our conclusion is that a die tends to produce more tools. Is this correct? Because our experiment and data set, we have more tools when we roll a die. So the conclusion is a die tends to produce more tools. But everyone knows that even elementary school students know that this is false, right? If we conduct another experiment, if we roll a die again, we could have different results, right? So these examples show decision-making process involves uncertainty. And we need to explain this uncertainty when decision-making. And actually, we already know that a die, so when we roll a die produces 2 ones in every 6 rolls. And we say this, the probability of getting 2 is 1/6. Indeed, if we roll a die infinitely many times, 2 appears once out of every 6 rolls. If a die is a fair die. And this is called the law of large numbers in statistics. So when can we confidently claim that our decision is true? How can we measure this confidence? So this is where the probability comes in. So when decisions are grounded in evidence, the concept of probability applies. In this case, statistics connects data, probability, and decision making, and we can evaluate the uncertainty in decision making based on statistics. In particular, probability distribution. So let's see how statistics measure this uncertainty. But before that, some of you may wonder, we live in the age of AI, and machine learning and deep learning methods are widely used as an essential tools for AI. Then, do we still need statistics for decision making? But they have the machine learning and deep learning methods and statistical methods, they are somewhat different. So the key difference is that there are goals and strategies. So machine learning and deep learning based methods are designed to focus on prediction. So with massive amount of data, these machine learning and deep learning based methods focus on impressive prediction performance. But the problem is that these machine learning and deep learning based methods are often called a black box. So this means it is hard to understand how or why they reach their final decisions. So it is hard to interpret the result. And this may raise some concerns. If we have questions about the fairness or reasonableness for the final decision, it is difficult to explain or correct errors. So this kind of machine learning and deep learning methods may be problematic when it is applied to high-stakes domain, such as education, taxation, or insurance. On the other hand, statistics measures errors. And actually, I like this phrase, statistics permits mistakes. even statistics is interested in mistakes because statistics treats a data as a sample from a population of interest, and data is obtained from a random experiment. So this is the key concept of statistics. Data is obtained from a random experiment. So in this framework, statistics can explain how reliable is the result, what is the margin of error, and how much uncertainty is involved. By the way, do you think this role is important? Because prediction performance of machine learning and deep learning based method would be much better than the prediction performance of statistical methods. Let me show an easier example. So there are two types of people. The first person says, because I have done it all, I know it all. So my answer is always correct. Don't doubt me. Just follow my direction. The second person says, I know this part well, but I'm not sure this part. Then who would you rather work with as a colleague? Because this first person seems like 꼰대, a person who has trouble communicating. Because this person says, my answer is always correct, don't doubt me, just follow my direction. So many people would prefer to work with this second person because this person seems more flexible, easy to communicate. Do you agree with this? You have to agree with this. Then I can continue this seminar, right? I'm the first person. Anyway, the second person says, this is what I know, but this is not. In other words, calibrated collaboration. This means uncertainty quantification. So quantifying uncertainty means it enables our model to say, I don't know. In this case, statistics reports uncertainty, like intervals, probability, not just a guess. So specifically, statistics quantifies uncertainty by the probability distribution. Does this make sense? But if you have questions, then how about ChatGPT or Gemini saying, I'm sorry, I don't know. Anyway, so let's see more specific example. So change point analysis. So change point detection is one of my research areas. So given the sequence of observations, change point detection tries to identify the time when the probability distribution changes. And in this problem, there are two situations, two conclusions. The null hypothesis is there is no change point. The alternative hypothesis is there is a change point in the sequence. And because we have two situations, two hypotheses, two conclusions, there are two types of errors, two types of mistakes. The first one is we falsely reject the null when the null hypothesis is actually true. And this mistake is called a type 1 error. The second one is we falsely accept the null when the null hypothesis is actually not true. This mistake is called the type 2 error. So when we make statistical decision, because we have two types of mistakes, it is ideal to reduce these both types of mistake, right? But unfortunately, these two mistakes are not independent. If we reduce one error, the other error tends to increase. And as you can see, type 1 error and type 2 error are not independent and they influence each other. So we need to choose more serious mistake. So which one is more serious? Type 1 error and type 2 error. So generally, type 1 error is more serious. Because the null hypothesis is the current status, so if we falsely reject the null, we should do something like creating a policy, changing the system, anyway, something new. And this incurs cost and time. But if we falsely accept the null, even if this is a mistake, there is nothing to do, right? So the type 1 error is more serious. And we are already familiar to this concept. This corresponds to the concept, the presumption of innocence. So in Korean, 무죄 추정의 원칙. So this means we treat a person not guilty until there is a strong proof that this person indeed did something wrong. Even in Korea, to prove guilt, this must be proved through three stages, right? A prosecutor feels very hard to prove guilt in Korea. This means the type 1 error is more serious. So, because the type 1 error is more serious, we first set an upper bound of type 1 error and then try to minimize the type 2 error. And the complement of the events of type 2 error is called the power of the test. So we first set an upper bound of type 1 error and then try to minimize the probability of committing the type 2 error, which means try to maximize the power of the test as much as we can. So we define the significance level alpha as the probability of committing a type 1 error. And we define the p-value as the probability of obtaining test results at least as extreme as the result actually observed under the null hypothesis. So if the p-value is small, this means the probability of getting more extreme results is small, which means we have the result that is less likely to happen under the null hypothesis, which means we already have the sufficient evidence to reject the null hypothesis. So if p-value is less than the significance level alpha, we can reject the null hypothesis. So for example, we set a significance level, the probability of committing a type 1 error to be 0.05, and the p-value of the test is less than or equal to this alpha. We conclude with 95% confidence that there is sufficient evidence to reject the null hypothesis. There is no change point in the sequence. Okay? And note that statisticians don't say we reject the null or the null hypothesis is not true. Instead, statisticians say we are 95% confident that there is sufficient evidence to reject the null. Very careful to make decisions because there is no 0 or 1 probability in real world. So, for example, consider distinguishing cat images and dog images. Machine learning and deep learning methods say this is a cat image, this is a dog image. Cat, dog, cat. But statisticians say this is a cat image, but this decision could be wrong, at most 5%. Okay? So statistics offers more explainable decision compared to the machine learning or deep learning models, right? So in terms of statistical perspectives, the most important thing is to control the type 1 error because type 1 error is more serious. So in order to measure and examine this type 1 error, we need to know the probability distribution of the test statistic under the null hypothesis. And next, after controlling the type 1 error, we need to maximize the power of the test. This is called the consistency of the test. So to this end, we should know the probability distribution of the test statistic under the alternative hypothesis. So, for statistical decision making, we need to know the probability distribution of the test statistic. So, statistical decision making, we should derive the probability distribution of the test statistic. And to this end, many statistical methods are based on specific assumptions on data. So for example, two-sample t-test, ANOVA. Most students know this, but even this two-sample t-test, ANOVA, we assume that the data follows the normal distribution, right? Or we assume some specific data structure, like graphical models, time series data, network data, and so on. However, in this big data era, the amount of data is so huge, and its form is so complex. So this kind of assumptions may not hold in many cases. So indeed, there are two types of statistical approaches. The parametric methods pose some assumptions on data. Data follows some probability distributions. Data has some network structure, and so on. But non-parametric approaches try to minimize assumptions on data or models. And my research area lies in developing these non-parametric approaches. So I have been developing non-parametric methods for analyzing high dimensional or complex data, such as A/B test, like two-sample test, testing whether two groups are different or not. Change point detection, testing whether a change point exists in the sequence or not. Association test, testing whether variables are independent or not. Spatial clustering, testing whether the target object, our interesting objects, are clustered or not. So in the remaining time, I am going to introduce one of my research areas, spatial clustering, titled A Robust, Scalable Case Statistic for Quantifying Clustering in Spatial Data. And this work was originally developed for applications to spatial proteomics. For example, we are interested in whether immune cell spatial clustering is associated with the cancer survival rate. But this work can be applied to measuring general spatial clustering and assessing whether the spatial clustering is associated with some outcomes of interest. So in terms of transportation research, like traffic congestion or mobility analysis. Actually, I don't know spatial proteomics as well because my collaborator is specialized in this field. But anyway. So we have two images. And for each image, we have two types of observations. The first one, this red one, is the target object, our interesting object. And the other one, this gray color, is background observations. And for these images, we are interested in testing whether the target objects are clustered compared to the background observations. So we have two hypotheses. The null hypothesis is there is no spatial clustering, which means complete spatial randomness, CSR, like this image. The alternative hypothesis is the target objects are spatially clustered, like this image. And for this problem, so it is common to represent the objects, counts, and locations in each sample, in our case, on each image, as one realization of a point process. And in this case, homogeneous point process model is widely used to assess whether counts are randomly distributed within the sample, within the image. And under this homogeneous point process model, Ripley's K, a popular metric from point process analysis, has been used to summarize this spatial organization. So we are going to use this Ripley's K to assess the spatial clustering of the target objects. So let's first see the Ripley's K. So let this NS be the total number of observations, and MS denote the number of target objects in image S. So the number of background observations is NS minus MS, because we have two types of observations in the image. Then given the radius R, the Ripley's K can be calculated from this formula. So here, this D, this means the pairwise distance between observation I and J. And this numerator is the image area. And here I, this means the indicator function. So this means if the distance between observation I and j is less than or equal to r, this indicator functions becomes 1, otherwise 0. And Eij is an edge correction. This edge correction accounts for the bias that occurs when the target objects at the boundary of the image have fewer neighbors than the observations near the center image. So, if two observations are close to each other, less than r, this indicator function becomes 1. So, if target objects are close to each other, this Ripley's K tends to increase. Okay? So, this Ripley's K explains the spatial clustering of the target objects. Indeed, a large value of this Ripley's K could be the evidence of spatial clustering of target objects. And given this background, we can define the degree of clustering. So let this K hat be the observed Ripley's K. And we compare this observed Ripley's K with the expected K under the null hypothesis of no spatial clustering, denoted by K0. Then, the degree of clustering can be defined as the difference between the observed Ripley's K and the null value of Ripley's K. Okay? And as I said, the Ripley's K tends to be large as the target objects are clustered. If this observed Ripley's K is greater than K0, we can say, which is the positive value of this K tilde, we can say spatial clustering within the image is inferred. Okay? And under the null hypothesis, CSR, it is known that this Ripley's K has a theoretical value of pi r square. So, the degree of clustering can be defined as the observed Ripley's K minus this theoretical value of K under the null, pi r square. And given this definition of degree of clustering, so this is a motivating example for this project. So, in this first image, we can see that the target objects are clustered compared to the background objects. And indeed, the observed Ripley's K is greater than the theoretical value of Ripley's K under the null hypothesis of no spatial clustering. And under the null hypothesis, CSR, observed Ripley's K is almost same as the pi r square, the null value of Ripley's K. And the problem happens in these two images because these two images have areas of spatial inhomogeneity because of kind of tearing or degradation. In this third image, we see that the target objects are spatially clustered, and indeed this observed Ripley's K is greater than the theoretical null values of Ripley's K, but this gap, the difference between the observed replace K and the theoretical null value is greater than this gap in the first image. So this means because of this, it is unclear whether this increased gap, increased difference, reflect the spatial clustering or some other reasons. And this phenomenon gets severer in this last image. We see that target objects are randomly spread out, but even in this case, observed replace K is greater than the null value of replace K. Okay? So we want to correct this bias. We want to improve these theoretical null values of replace K. So we need corrected null value of replace K regardless of spatial characteristics, spatial homogeneity or inhomogeneity. In other words, we develop a method that adapts to the inherent spatial characteristics of the data set rather than relying on the predefined assumptions about spatial homogeneity. So to this end, we generate an empirical null distribution through permutations. So to understand this, let's first see the permutation test. So suppose that we are interested in whether two groups are different or not using the test statistic T. And this is a procedure of permutation test. First, we keep the observed values fixed, but randomly shuffle the group labels, randomly permute the group labels. So because we are interested in comparing these two groups, there are two group labels, and we randomly permute these group labels. And for each shuffle, each permutation, we compute the test statistic T. So for example, if we are interested in whether two group means are different or not, the natural test statistic is the sample mean difference. So in this case, for each permutation, we compute the sample mean difference given the new label. And we repeat this many times to get many test statistics. And the rationale behind this test is these many T's approximate the distribution of what we see if there were no real difference, the null hypothesis. So then,
so when you say you shuffle the groups, two groups, means you have samples, you change the labels for the samples?
The labels of the samples. The data is fixed. We only change the labels of the data. And for each permutation, we calculate many T's. Then we can construct this empirical distribution of these T's. And we call this the permutation null distribution. Then we denote this T obvious by the observed statistic from the real labels. And if T obvious sits in the extreme tail of the permutation distribution, the observed difference is unlikely to chance alone. So this means this area refers to the p-value of the test. And if this p-value is small, we can reject the null hypothesis. And this permutation test is a distribution-free test. We don't assume anything on data. We don't assume the normal distribution of the data. We don't assume some specific structure on data. We only just permute the labels, right? We just permute the labels of data, and we can get the permutation null distribution, and we can get the p-value of the test. So this is the permutation test. So from this, we try to leverage the first and second moments of the distribution of Lipinski under all possible permutations of observation labels. So in other words, the first moment means the expectation of K. This provides an empirical estimate of null value of K for each image. And the second moment means the expectation of K square. This enables the construction of the test to determine whether Lipinski deviates from the null value of K for each image. So from this, we can define the new degree of clustering. So this is the original definition of degree of clustering. The observed K value minus the theoretical K value under the null hypothesis. And it is known that this is pi r square. But we substitute this theoretical K null value with this. And this is the expectation of Lipinski under the permutation null distribution. And we expect this expectation of K under the permutation null distribution to correct the biases introduced by spatial characteristics, spatial inhomogeneity. And we call this KAMP, K adjustment by analytical moments of the permutation distribution. So given this new definition of degree of clustering, let's get back to the motivating example. So here, this green line, KAMP, this refers to this one, the expected value of K under the permutation null distribution. And we see that in these two images with spatial homogeneity, we see that KAMP is almost the same as the theoretical K value under the null hypothesis, right? But in these two images with spatial inhomogeneity, we see that KAMP is slightly greater than these theoretical null values of K. So this means KAMP effectively removes the spatial inhomogeneity while preserving the signal from spatial clustering. And indeed, in this image, when the target objects are randomly spread out, the null hypothesis, KAMP is almost similar to the observed K. This means KAMP can correct the bias from spatial characteristics compared to the theoretical null value of K pi r square. And in addition to this new degree of clustering, the next step is the hypothesis testing procedure. And given the image S, we test the null hypothesis of no spatial clustering against the alternative hypothesis of spatial clustering. To do this, we use the standardized Lipinski. Standardized Lipinski using the expectation and variance of K under the permutational distribution. So to calculate this standardized test statistic, we need to calculate this expectation and variance of K under the permutational distribution. To this end, like permutation test, we permute the labels of target objects and background observations. Because we have two types of observations in the image, we can permute these labels of observations, then we can calculate this expectation and variance of K. But when the sample size is very large, this permutation is time consuming. So suppose that we have 10 observations. And in order to calculate the exact expectation and variance of K, we need 10 factorial permutations, right? So when the sample size is large, this permutation is very time consuming. So we try to derive the analytical expressions of this moment under the permutational distribution. So to this end, we represent the replace K using this new indicator function. So here, Wij is this distance term. And here, in this new indicator function, Gi is 1 if on observation I is a target object and 0 otherwise. Then, with this new indicator function, we can apply the combinatorial analysis to calculate the analytical moments of this K. So under the permutational distribution, analytical expressions for the expectation and variance of K under the permutational distribution can be derived like this. So here, this F term is related to the sample size, and this R term is related to the distance. So once the data, the image is given, this expectation and variance of K can be immediately calculated without permutations. So we can save the time. And once we calculate this standardized test statistic, so let this Wij tilde be the centered Wij, where this W bar is the overall average of this distance. And let this Wi dot tilde be the sum of this Wij tilde with respect to the index I. Then we derive the asymptotic permutation null distribution of the test statistic under these two conditions. So under the permutation null distribution, as the sample size goes to infinity, the standardized test statistic converges in distribution to the standard normal distribution under these two conditions. So we derive the asymptotic permutation null distribution of this test statistic. So this means, given the significance level of alpha, without conducting actual permutations, we can reject the null if the test statistic is greater than Z critical value. This Z critical value can be obtained from the standard normal distribution. So this means we can immediately obtain the p-value of the test once we calculate the test statistic without actual permutations. Okay? Does this make sense? So let's see some simulation result. So two cases. no spatial clustering, and for each case, we have two spatial conditions, spatial homogeneity and spatial inhomogeneity. And let's first see the normal approximation of the test statistic. So this figure shows the normal QQ plus of the test statistic, this CK. And here, this lambda represents the total number of samples, and this P represents the portion of the number of target objects out of the total number of samples. And we see that the permutation null distribution of Z, the standardized test statistic, can be well approximated by the standard normal distribution. And we examine the performance of the test. So we compare our method with some method like K, the original Ripley's K, and inhomogeneous variant of Ripley's K proposed by this author, and the Ripley's K from actual permutations. And CAMP is our new approach. And we hope that CAMP is almost similar to this POM, right? And this figure shows the testing results under the null hypothesis. So no spatial clustering with spatial homogeneity, no spatial clustering with spatial inhomogeneity. And we see that except for this inhomogeneous variant of Ripley's K, the degree of clustering is almost zero because there is no spatial clustering. But under the null hypothesis with spatial inhomogeneity, this original Ripley's K and the inhomogeneous variant of Ripley's K, the degree of clustering is not equal to zero. So this means the Ripley's K interpret this spatial clustering larger than the original spatial clustering degree. On the other hand, the Ripley's K actual permutations and our analytical version, the degree of clustering is almost zero because there is no spatial clustering. And under the alternative hypothesis, the spatial clustering with spatial homogeneity, spatial clustering with spatial inhomogeneity, we see that except for the inhomogeneous variant of Ripley's K, the degree of clustering is greater than zero. And even in this spatial clustering with spatial inhomogeneity, these three methods show the spatial clustering. But you can see that this original Ripley's K is slightly greater than the degree of clustering of permutation-based method and our method. So this means this original Ripley's K inflates the spatial clustering, overestimate the spatial clustering because of this spatial inhomogeneity. And this is the result of hypothesis testing because we carry out the permutation test. Under the null hypothesis, we see that the permutation-based method of Ripley's K and CAMP control the type-1 error well. And this is the case of alternative hypothesis. We can see that the permutation-based method and our method, the power of the test increases as the sample size increases. And we see that our analytical version behaves almost similar to the actual permutation-based method. But compared to the actual permutation-based method, so this figure shows the computational time of degree of clustering. because we propose to use the analytical version of the moments of K under the permutational, we see that our approach is much faster than the actual permutation-based replace K method. And after quantifying the spatial clustering, the next goal is to assess the association between spatial clustering and survival rate across images. So for example, we propose to use this new degree of clustering in the Cox proportional hazard models. Then this is the Cox proportional hazard model with new degree of clustering. And by the standard word test, I will omit here, we can get this information. For example, if this beta K is 0, this means the spatial clustering of target objects is not associated with the survival rate. And if this beta K is greater than 0, this means the spatial clustering is proportional to hazard, which means spatial clustering decreases the survival rate, like cancer survival rate. And this negative beta K offers the opposite result. So to sum, we proposed the CAMP, a new method for quantifying spatial clustering while addressing the spatial characteristics. And this new degree of clustering successfully corrects the bias introduced by inhomogeneous samples. And by providing the analytical expressions of these moments of K, we can reduce the computational time without permutations. And by proposing the hypothesis testing and the liminal distribution of replace K, we can carry out the hypothesis testing for the spatial clustering. So this is what I prepared today. Thank you.
Great. Thank you very much. Any question? Don't be shy. Any question? Sharon, would you like to start?
Yes.
Thank you for your great presentation. That was so hard to follow your presentation, but I have one question. The main novelty is I expect is you can calculate the moment of the implicit case expectation without permutation test.
Yes.
And then I remember you assume nonparametric approach.
Yes.
I'm curious about this expectation value can be applied for another value, like I'm not sure of the example without implicit, but we can use this concept into another statistical things.
Yes. Yeah. So as I said, I have some research areas, change point detection or two-sample test. And in terms of non-parametric methods, the one way to adopt the non-parametric approach is to use this permutation test. So I'm not sure if you have heard the bootstrap approach. So bootstrap approach is almost similar to this permutation approach. So permutation is the sample without replacement, but bootstrap approach is sample with replacement. So bootstrap test or this kind of permutation test is one approach to carry out the non-parametric test. But in this case, we may be able to derive this kind of analytical expressions of moments of the test statistic. And indeed, in my other areas, change point detection and two-sample test, when I want to carry out the permutation test, I'm trying to derive this kind of analytical expressions for the moment, because actual permutation is very time consuming when the sample size is very large. So the one disadvantage of permutation test is the computational time. Any other questions?
Yeah, I have a couple of questions. Thank you very much for great talk. It's just so fascinating. The first question is like a bit technical. I'm not too sure I'm in the position to ask technical questions, but you have, when you calculate the Ripley's K value, you use radius R.
Yes.
But it seems like it depends, the results, chemical results also depend on
Yes,
how
yes.
determine R. So how sensitive is the count statistic to this choice of R?
Because there is no specific rule to the choice of R. So empirically, heuristically, we propose to use 0.2 times the length of image.
So it's a heuristic.
Yes.
The computation now that in homogeneity, so you generate the empirical null distribution to permutation
Yes.
to correct for inhomogeneity.
Yes.
That's what I understood.
Yes.
And by permitting the labels of target objects and background observation, are we implicitly assuming that the background structure is independent of the target structure?
So actually, the independent assumption does not need in this permutation test. So actually, the only one condition for this permutation test is the exchangeability of observations.
I see.
I omit that concept, but we assume that observations are exchangeable. In this case, independence does not affect, the dependence does not affect the performance of the permutation test.
It's not easy to grasp why this commutation test improves intuitively improve the issues with inhomogeneity. Can you explain in an intuitive manner why having this commutation test can improve?
So I think first this theoretical null value or pi r square. This assumes the spatial homogeneity. That's why this theoretical null value cannot correct the bias from the spatial inhomogeneity. Then why does this permutation approach correct the bias? I'm not sure, but because, as I said, this is kind of distribution-free test, so this permutation test does not assume any conditions on the data structure. So probably this kind of approach, robust method to capture this difference. So, but I'm not sure the actual reason why this permutation test can correct this bias.
So intuitively, because you mentioned in the original approach, we assume homogeneity.
Yes.
So therefore, we have the analytical K0. But in this case, we use the data, which actually captures the structure, spatial structure of the inhomogeneity. So by having commutation test, the distribution actually captures the homogeneity. So therefore, having the, p-value test, we can actually capture the spatial structure of this data. Therefore, we might be able to improve. That's what I think.
Yes, hopefully.
But I'm not 100% sure.
Yes. Okay.
And in terms of the computational complexity, So you are avoiding actual computation, which is like exponentially, the computation complexity explodes
Yes.
as the size increases.
Yes.
But if we see the calculation, I'm not 100% sure I captured it correctly, but when you calculate R3, we have 4 sums, which therefore I assume that the computation complexity is proportional to the ns power to the 4, which is still quite a lot.
Yes, yes. Yes, that is the one disadvantage of this camp approach. So we are also working on this. We continue to work on this project to reduce that computational time. So now we are adapting the block image approach. So we divide the total image into some several blocks, and then we apply this camp for each block, and this can reduce some computational time. So now we are working on this.
So if we see the result of the comparison of the computation complexity with the original computation.
Yes.
Here, interesting enough, I thought if we implement computation method, then when we size the number of samples to almost 2.5 times, then the computation complexity significantly actually increases in the original computation method, but it stays very similar, which is quite interesting. Whereas CAMP, if we compare these two, it's I think it doesn't scale linearly; it scales like very exponential. Whereas computation doesn't. So it's
So because here we applied only 1,000 permutations to calculate this, regardless of the sample size. Of course, these 1,000 permutations are not enough to get the exact permutation moments of K. But anyway, here we only apply 1,000 permutations. We hope these 1,000 permutations can approximate the exact expected value of K or variance of K under the permutational, but theoretically these 1,000 permutations are not enough.
sure. Very interesting, and I quite like the approach. Are you trying to also combine this machine learning approach with the statistical approach? Or is it purely focusing on the second part?
I purely focus on statistical approaches
I see.
because many people are working using the machine learning and deep learning method. So a few person should work on the statistical method.
I see. Blue ocean. Okay, great. Any other question? Too easy to understand. To me, very difficult to understand. Maybe very philosophical. So anyway, we have no questions. Can we? Yeah.
Thank you for your insightful presentation, and I have a quick question. My research interests lie in design optimization using AI. So, in many design optimization, the features or behavior descriptors are manually defined by humans rather than discovered from data. So, given that these human-chosen features may not reflect the true underlying structure, so do you think permutation-based tests could serve as a nonparametric way to evaluate whether our chosen features are actually meaningful rather than arbitrary designs?
I think so. Yeah, we can apply this approach because the most different thing of statistics compared to other approaches is statistics assumes the data has the probability distribution because data is obtained from the random experiment. So anyway, statistics should assume the distribution of the data, but in many cases, we don't know this information. And one way to solve this problem is to apply this kind of non-parametric approaches. But I'm not sure.
Any other question? Just one more question, sorry. In this case, you are concerning about the spatial inhomogeneity.
Yes.
Do you think is it possible to implement similar approach for the different inhomogeneity? For example, when we have some data, there are certain kind of like behavior spatial, some different distribution influencing to the spatial behavior.
I'm not 100%, but hopefully this approach may be able to solve that issue, but I'm not sure. Yeah.
Okay, no more questions? Then once again,
Thank you.